D5. Choose and verify permanent corrective action, PCA. Based on the root cause identified in D4, we will come out all the possible corrective actions. The corrective action plans should include both corrective actions to prevent reoccurrence, and corrective actions to prevent escape. There might be multiple corrective action plans, or approaches. Perform risk assessment on each of the corrective action plan. Develop FMEA to anticipate the issue, before implement the corrective action, if necessary. Based on risk assessment, make a balanced choice for PCA. Ask if the PCA makes sense in relation to the product cycle plan. Is it worth for company to invest $1 million in enhancing the test solution by knowing the product will end of life in 3 months? Similarly, if we know the product will be terminated within next 2 quarters, do we still want to spend effort in redesign it? Whenever possible, have the customers in choosing the solution. Especially when you do not have the perfect solution. Share the pro and con of each solution openly with customers. Help them to understand the risk of each and involve them in choosing the solution, which best for the business. Quantitatively confirm the PCA will solve the problem through the prototype or pre-production programs. Verify the corrective actions relevant to escape prevention is effective through false injection. False injection is a tactic to test the effectiveness of inspection or testing by smuggling some random failures without awareness of the inspector or tester. This is used to verify the effectiveness of detection. Lastly, we need to check if there is any side effect. We need to anticipate failure of the solution and develop contingency action. While exploring the permanent corrective action, PCA looks for the industry, if the solution is already available. How other groups solved similar problem. How similar problem was solved for other products. These are the typical corrective actions to prevent reoccurrence. First one. Change the hardware, or software design. For example, modify the mold. Second. Recharacterize, or optimize the process. Third. Preventive maintenance. The use of shop floor control system. To control material movement. To error-proof wrong material, or wrong process parameter, from being used. Enhancing environment control, which covers humidity, temperature, noise, illumination, or brightness. Another example of corrective action is through industrial engineering, i.e. approach. That is, to control operator movement, or even relay out the line. The areas to be considered include sequence of operation, ergonomic, and line balancing. Visualize the system is another good example for corrective action. The tactic for visualization includes color coding, visual aid and work instruction. For examples, we can use colors of traffic light, red, orange, and green, to label reject products, pending testing products, test accepted products respectively. Operator retraining, and enhancing product handling, are also typical corrective actions. When time permits, I will come out video to explain the detail for each of these corrective actions. Let's move from corrective actions to prevent reoccurrence to corrective actions to prevent escape or increase detection. The typical corrective actions to increase detection include automate the testing, use of go-no-go gauge, enhance manual visual inspection, use of audio or visual effect to help testing. For example, trigger the buzzing sound, or turn the monitor screen to red color, to attract the attention of the operator when there is a reject. SPC control chart is another good approach to monitor process stability. It will trigger if there is process abnormality. We can use statistical sampling plan, or theory, to define the sample size. First article inspection, also known as first piece inspection, is approach to inspect the very first few pieces of production units in detail, before moving into mass production. As a minimum, we need to do this during the first NPI build. NPI stands for New Product Introduction. There are companies practicing first article inspection for every work order, or even every beginning of shift. Some processes need a special trained skill set to set up the machine. Some companies set a policy that the need of independent party to inspect the setup to ensure it was properly done before release to production. We call this machine setup buy-off. The effectiveness of inspection or tester could be verified through tactic of GRNR, gauge repeatability and reproducibility. GRNR itself is a big topic. When have chance, I will come out a video for this too. Before we end the D5 section, allow me to introduce you a table format for solution selection. There are times, the solution is not straightforward, not only single corrective action is available. We are forced to consider all the alternatives, and choose the most appropriate and make business sense. Let's say we have a customer reported functionality issue. Your failure analysis team has concluded that it was due to design marginality issue. When the value of a specific capacitor is at marginal spec limit, though it is still within the limits, the product might experience intermittent issue after operated longer than 2 hours. In another word, this is design issue. The spec limit is a bit too wide, though the capacitance for the selected component is within the ±5% of nominal value, which is limit per industrial standard. We might still observe certain failure rate. This happened while the capacitance value is near to the spec limit. To tackle this, firstly, list down all the possible PCAs. The available alternative solutions are: tighten internal test limits, tighten test limits at supplier, change to supplier XXX, redesign the product, add precaution instruction, not to use more than 2 hours, into the usual manual. Next, is to document down the business impacts, based on the 3 measurable characteristics: quality and reliability, failure rate, setup cost and cost per unit, expected delivery date. For the first alternative solution, tighten internal test limits to screen at product level. Even with internal screening, we still expect the quality level at about 50 dpm SKP. You might want to watch back the first video to help you recall what is the meaning of dpm. The 50 dpm could be contributed by the tester accuracy, or more exact, tester repeatability issue, while the measurement is at marginal spec limit. And reliability is estimated as 1% failure rate per the warranty period. Here, we use the question mark to indicate these estimations are just experience-based, an engineering gut feel. We assume it needs only minimum effort from test engineering to revise the test limit. Hence, the setup cost is negligible. Since this is product level screening, instead of component level, if there is reject, we need to rework the product by replacing the component. And the rework cost per unit is calculated and estimated at $1. Here we use the at symbol to represent they are empirical estimations. That is, through industrial engineering and or finances calculation. Since this solution is within internal control, it could be delivered within 2 weeks. Second alternative solution is tighten test limits at supplier. Since this is screening at component level, which will provide us accurate screening, both quality and reliability are expected at 0 dpm. Supplier might not charge for setup cost for this case, but will incur 80 cents per unit for handling this special screening limits, which are different from the off-the-shelf industrial standard. The total process, including the negotiation with supplier, might take about a month to receive the first batch of materials. The third proposed solution is change to new supplier, XXX. Anyhow, this is new supplier, which we never engaged before. We do not have information to estimate the quality and reliability level. This is off-the-shelf component. Hence, no setup cost charged by supplier. The motivation of this proposal is the price is even cheaper than current supplier by 10 cents. Due to new supplier, it might take as long as 3 months to qualify the component and certify the supplier. Next alternative solution is improve the product design. Based on engineering judgment, this is ideal solution for both quality and reliability. The setup cost is about $10,000. This includes the effort from design engineer, cost of modifying the tool, spin the PCB, etc. But, when come to manufacturing, there is no additional cost to build each unit. Since this is design change, it might involve tool or mold change. We might even need to resubmit the product to regulatory for approval. The total process will take about 6 months. The last alternative solution is add precaution instruction into the instruction manual. Advise user not to use the product longer than 2 hours. Since we are not doing any improvement, the quality and reliability information is not relevant. If you want, you can fill up the quality and reliability level reported by customer here. The setup cost is estimated at $1,000, basically is the cost to change the print plate, which quotation still pending from supplier. There is no additional unit cost for printing new instruction manual. Supplier committed to deliver the first batch of manuals within 2 weeks. With info for all the measurable characteristics available, we can now go ahead to choose the PCA. Firstly, we rule out the last solution, since this might cause huge customer dissatisfaction. Especially, when your competitors do not have similar issue. Here, we put a red negative sign here to indicate this. By knowing the product is going to be end of life in next 12 months, we also dropped the proposal to redesign the product, since this takes too long to implement. No ROI, return on investment, based on forecasted volume. For proposal of changing supplier, we use orange, equal sign to indicate, tentatively bin the proposal. 8D team agrees to choose, tighten test limits at supplier, as permanent corrective action. To do so, we need to assign a new part number for components which screened with new limits. This is to prevent mixing and control at supplier. Anyhow, this solution takes us 1 month to receive the first batch of materials. Our customer might not be able to wait for it. They are awaiting our parts to launch their new product. So we also implement tightening internal test limits, as interim solution, while awaiting the new screened materials from supplier. I like this format very much, since it helps me to visualize to stakeholders, include management, how I come to the conclusion, on which permanent corrective action was chosen. D6. Implement and validate PCA. Before we move into the detail of D6, would like to draw your attention on the keyword used in D5 and D6 respectively. That is, we use the word verify in D5, while validate in D6. So, what are the differences between these two? Verification is done through artificially simulate the solution. For example, through the prototype or pre-production programs, instead of changing the production mold. Fault injection is also a tactic to verify the effectiveness of detection. Verification generally could be done through small quantity build. While for validation, normally it is through mass production's quality indicator. There are 3 main steps in D6. Define action plan for chosen actions. Communicate the plan to all stakeholders. Validation the effectiveness of actions. As a minimum, action plan must include description of action, owner, or responsible party, timing, or target completion date. Sometimes corrective actions can be implemented by phase, especially when permanent corrective action cannot be put in place immediately. Team to define standard identification, or marking for products produced after implementation of corrective action. Once plan was defined, communicate to all stakeholders. The best communication way is, document down the procedure or specification, to ensure consistency in implementation, and avoid miscommunication. Remember to inform the customers the implementation date for the corrective action, and how they can identify the products which produced after implementation of corrective action. The last step in D6 is validation the effectiveness of actions. The objective is to document down the evidence that the corrective actions are effective. One of the best damage control is to show your courtesy to customer. Ensure they are able to reach you when they want to voice up their concern. Keep them in contact. Obtain their feedback on the effectiveness of corrective action, if necessary. Examples of evidence for effectiveness include trend chart, SPC chart, and Pareto chart. When we need to do validation for process, design, software, or hardware change, remember to factor in the lead time for validation. We might need to resubmit the product for regulatory approval. And pre-alert to customer on the change, and involve them in both verification and validation. If you see value in this video, please click on the thumb up, and share. This definitely will motivate me to make more quality video related to this. Please click on subscribe too, this will ensure you would not miss any subsequent videos. Before we end the session, let's close our eyes, observe a moment of silence, pray with your own respective religion. May the community full of peace, and may the world free from disasters. Looking forward to see you in next video. Thank you.